Have you ever spent a week running what you thought was the perfect experiment, only to waste the next 2 weeks absolutely drowning in a data swamp? Yeah. If you're tired of wrestling with spreadsheets just to see what your results are trying to tell you, then you are in the right place. We're about to turn that swamp into a superhighway for analysis.
And this, right here, is the core mistake. It's the one thing so many of us do. We treat a spreadsheet like it's our lab notebook, a place to just jot down notes and numbers. But that one single habit, it costs us days, sometimes even weeks, of just tedious, mind-numbing data cleaning. It is time for a huge shift in how we think about our data.
See, your data sheet isn't a diary for you. It's a structured input for a computer. When we set it up like a diary, it's messy, it's manual, it's slow. But when we format it for the machine, well, we go from wrestling with this tangled mess to getting crystal clear insights in minutes. It's literally the difference between chaos and clarity, between slow and fast. So, to make this all real, let's dive into a frustrating, and I'm sure all too common, lab nightmare. We're gonna go chase a ghost in the machine, the dreaded assay failure.
Okay, imagine this. You're developing a really high-sensitivity ELISA, but nothing is working. The background signal is through the roof. Your controls are drifting all over the place. Your standard curve, it's basically useless. So what is it? Is it the blocking buffer? Maybe the wash steps? It really feels like there's a ghost in the machine, and we are going to design an experiment to find it.
So how do we catch this ghost? Well, we need a better toolkit. Just recording the raw data is like trying to fly a plane by only looking at the altitude. I mean, to get anywhere, a pilot needs airspeed, fuel, a heading, and in the lab, we need our own dashboard of calculated responses.
First up, signal to background. A high signal is totally meaningless if your background noise is also high. It's like trying to hear a whisper in a really loud room. This ratio, comparing your max signal to the noise, is the #1 health indicator for your assay.
Next up, sensitivity. Look, running a full validation is way too slow when you're in the middle of development. So we use a proxy for the limit of detection. This gives us a reliable snapshot of how sensitive our assay's getting as we tweak things like antibody concentration or incubation time. Technical precision is absolutely non-negotiable. We measure it with the percent coefficient of variation, or percent CV. Here's the deal. If your replicates vary by more than, say, 15%, your data is just too noisy to trust. Any optimal result you think you found could just be random chance. This metric, right here, keeps your science honest. And for those of you in high-throughput screening, there's the Z-prime factor. This is the gold standard. It elegantly combines your assay's dynamic range and its variation into a single score. Think of it as the ultimate report card for a robust, reliable HTS assay.
Okay, we have our metrics, we know what to measure. Now let's build a practical plan for the bench. How in the world do we fit a powerful ghost hunting experiment onto a single 96-well plate? 80, that's it, that's the magic number. After you account for your standard curve and all your controls, you have 80 wells to play with. This isn't some infinitely complex problem, it's an 80-well battle plan.
And the math is way simpler than you think. You've got your standard 96-well plate, take out 16 wells for your standard curve, that leaves you with 80 wells for the actual experiment. Now, a really powerful 5-factor experiment, that only needs 64 wells, if it's perfectly. And just like that, you've designed a world-class experiment. But here it is, the one rule you can never, ever, ever break: randomize. Do not run all your low-temp samples first, then all your high-temp ones. Why? Because what if your plate reader warms up over time? Then you won't know if the effect you're seeing is from temperature or just from time. Randomization is what protects your results from all these hidden variables. Okay, we've got the metrics, we've got the plan. Now for the secret weapon, the data sheet format itself. This is what unlocks the speed we've been talking about. This is what we call the tidy data format, and the rule is incredibly simple. 1 observation per row. That's it. 1 well gets 1 row. Don't format your sheet to look like a plate grid. That's for human eyes. This long format is for machines, and it is what allows analysis software to instantly understand every single variable in your experiment. And hey, here's a pro tip that will save you from a massive, massive headache. Save your file as a .csv, a comma-separated values file. This one simple step stops spreadsheet software from helpfully auto-correcting your gene or protein names into calendar dates. You know what I'm talking about. It's a classic, frustrating problem, and this solves it. Finally, even with a perfect plan, the real world has a way of interfering, doesn't it? So let's quickly cover the 3 Assay assassins that are just waiting to ruin your data. First up, the edge effect. Wells on the outside of the plate evaporate faster. That concentrates your reagents and can artificially boost the signal. So if all your best results are happening to be on the edge of the plate, you might be looking at a mirage, not a real effect. Assassin number 2, the Friday effect, also known as operator bias. Look, different people just pipette differently. It's a fact. If 2 people work on the same experiment, you have to include operator as a factor in your datasheet. You might just find that one person's technique is introducing a ton of variability. And last, reagent aging. Over the course of an 8-hour experiment, your precious reagents are degrading on the bench. If you just track the time since they were prepared, you can actually measure if your assay is robust enough to handle a long run. And this brings us all the way back to that central idea. When you stop treating your data sheet like a diary and you start treating it like a structured input for a machine, you stop fighting with data and you start making discoveries. So take a hard look at your own process. Is your data sheet hiding your next breakthrough?